All right, now we do infinite series, chapter 10, section 2. Sorry it took so long in my earlier class. What is infinite series? Infinite series is the sum of an infinite sequence of numbers. So let's say the sequence of numbers is A1 plus A2 plus A3 dot 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 A sub n dot 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 and keeps on going forever because it's an infinite series. It doesn't stop. All right. Now, so we're looking at this, we have something that's called the partial sum. Or we can look at the nth partial sum. It's the sum of the first n terms of the sequence. So what does that mean? What if we had this is our sequence. So when n is 1, we get 1. When 2, 4, 8, 16, 32, and so on and so forth. So here are the partial sums. So for the first one, it's just well, S sub n x out. So the first one, S is 1. That's the first term. Value is 1. The second term is the first two, 1 plus 1/2, which is 3/2. The third term, which is the first 3, so common denominator is going to be 4. So it's 4/4 plus 2/4 plus 1/4. It's 7/4. And so on and so forth. And the nth term is going to be all the way to 2n minus 1. And the value is 2n minus 1 over 2n minus 1. The reason we do this is because, like we did up here, we had to add up the numerators. So in the third one, we had 2 to the third is 8 minus 1 is 7. 2 to the third minus 3 minus 1 is 2 is 4. All right, so here's the equation. It's going to be 2 minus 1 This is going to be 2 minus 1/2. This one's going to be 2 minus 1/4. And going on this one, it's going to be 2 minus 1 over 2 minus 1. That's going to give us the answer. So for this one, our S sub n is 2 minus 1 over 2 n minus 1. But that's what we're looking for in this sequence, this part. So the definition. Using the last example. Adding the lengths of the sequence 1, 1/2, 1/4, 1/8, 1/16, 1/32, and so on and so forth. We approach the number 2. That's what we're looking for now. So this keeps on going forever and ever. So we're looking at, given a sequence of numbers, like this. An expression of the form a1 plus a2 plus a3 plus dot dot plus a sub n plus dot 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 is an infinite series. It keeps on going forever. The number a sub n is the nth term of the series. The sequence, because it's a set defined by S1 is A1, S2 is A1 plus the partial sums. S3 is A1 plus A2 plus A3. Sn equals A sub 1, A sub 2, A sub 3, dot, 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 plus A sub n, and so on and so forth. And the sequence is defined by this sequence is called the sequence of partial sums of the series. If the series approaches a finite number, we say the series converges and the sum is L. What that means is as we add our numbers in our sequence in our infinite series, if that sum as it goes to infinity, if that sequence, the sum equals some number equals L. Else, if the sequence of partial sums of the series diverges, i.e., it does not converge. So yeah, we can write the summation anyhow we want to. Let's first look at geometric series. We have two types. We have arithmetic and geometric series. Geometric series have a common ratio, meaning there are multiples of each other. So A plus AR plus AR squared plus AR cubed plus ARN minus 1 ARN . So this sequence can be summed up as I equals 1 to infinity of the common ratio R n minus 1. So for example, if we had the sequence we just had, 1, 1/2, 1/4, 1/8, ... So this is A1, A2, A3, A4. We look for a common ratio. That means A2 divided by A1 will have the same thing as A3 divided by A2, which is the same thing as A4 divided by A3. Let's see. So 1/2 divided by 1 is 1/2. That's the first one. So it's 1/4 divided by 1/2. Take the top fraction, leave it alone, multiply by the flip of the bottom. The 2 and the 4 cancel, so we have 1/2. So far, so good. Then I go to 1/8 divided by 1/4. Take the top, flip the bottom. So the common ratio R is equal to 1/2. Again, if the partial sum diverges, then the whole entire one diverges. If it converges, it converges. So if the absolute value of the common ratio is less than 1, the geometric series converges to A over 1 minus R. And then conversely, if it's greater than or equal to 1, it diverges. Because it keeps on going forever and ever and ever and ever and ever and ever. Let's look at an example. Example 1. The geometric series with A equals 1 over 9 and R equals 1 over 3 is 1 over 9 times 1 plus this is A, this is AR squared, so it's 1 over 9 times 1 over 3, 1 over 9, 1 over 3 squared, that's about, so it's 1 over 9, 1 over 27, 1 over 3 squared is 9, 81. Formula A R minus 1. So the sum of our sequence as n goes to infinity A is 1 over 9. One over 3. That equals A 1 minus R, which is 1/9, 1 minus 1/3. Take the top, flip the bottom. Okay, example 2. The series starts from 0, goes to infinity of -1 to the power n. So when n is 0, we get 5. When n is 1, we got negative 5/4. When 2, it's 1, so it's 5/16. Negative 5/64. And so on and so forth. It alternates. So A is the first term. One minus R is, so A is 5. R is negative 5/4/5. Negative 1/4. Plus 1/4. 5/5/4. So it converges to 4. All right, so once we have the sequence, we just find the common ratio and go from there. Example 3. Okay, let's see what it says. You drop a ball from a meter above a flat surface. Each time the ball hits the surface after falling a distance of h, it rebounds a distance of rh, where r is positive but less than 1. Find the total distance the ball travels up and down. Okay, so find the distance it travels up and down. So what does S equal? It equals to the first one, which is A, how far it's dropped. Then it's goes up and down, so it's AR happens twice. Then twice AR squared. Twice AR cubed. Twice AR N minus 1. So we start with A with 1. All of these have 2 A and R on it. Terms. We have A minus AR plus 2AR over 1 minus R. AR minus one of those, so it's A plus AR, 1 minus R. So that's. A is initial height and R is the rebound. Less than 1. Yeah, so that's it. Example 4. Express 5.23 as the ratio of 2 integers. So what do we have? So 5.232323 is equal to 5 plus, since these are in 2, so it happens 23 over 100. 23 over 100 squared. 23 over 100 cubed. Because they each happen in pairs of 2. So this is 100. That's another 100. That's another 100. So each of them have 23 over 100. 1 over, 1 plus 1 over 100 plus 1 over 100 squared. 1 over 100 cubed. So this tells us that my A is 1 and my ratio is 1 over 100. So we get 5 plus 23 over 100. That's 0.001, 0.01, 0.0001. So A1 minus R. So A is 1, 1 minus 0.01. 1 over 0.99. Three times 100 times. There's my answer. Which is equal to 523.99. Is the denominator. 495 plus 23 is third to 218. That's the answer. That was a painful one. Example 5. Find the sum of the telescoping series. And so 1 over n plus 1. All right. Let's look at this equation. We'll split up the denominators. Because we need to get rid of the n factor on top, so that's why I subtract it. So this n equals 1 to infinity of 1 over n plus 1 is the same thing as summation 1 over n we could split them up or we keep it together. We do 2 summations. So let's look at the partial sum. So when n is 1, we get 1 minus 1/2. Then this is n equals 1, n equals 2. So you get 1/2 minus third, 1/3 minus 1/4. And it's going to be 1 over n minus 1 over n plus 1. So we see that everything intermediary cancels, so we have 1 minus the last term. Because everything else in the intermediary cancels. So our sum becomes this. So as n goes to infinity, S sub n, this goes to 0. So therefore, the summation as n goes from 1 to infinity equals 1. See how many more we got? Oh, done. The nth term test for a divergent series. Okay, so as it says, one reason that a series may fail, may diverge, may fail to converge, is that its terms don't become small, they increase. So if the series increasingly gets larger, of n plus 1 over n. So when n is 1, we get 2 over 1. When n is 2, we get 3 over 2. We get 4 over 3, 5 over 4. So it's n plus 1 over n. So here's 2. What will those two become? 9 plus 8 over 6. That's so each of these terms gets bigger and bigger and bigger. So for a series to converge, the limit as n goes to infinity of the sequence must go to 0. If the summation of that sequence converges. Let's talk about theorem 7 first. If the sequence as n goes to 1 to infinity of a sub n converges, then a sub n goes to 0. If the summation converges, then a goes 0. Else, if the summation of the sequence diverges, then the limit as n goes to infinity of a sub n does not equal 0. So what this one says, the limit as n approaches infinity of a sub n equals 0 if it doesn't equal 0. Example 7. The summation as n goes from 1 to infinity of n squared. So the limit as n goes to infinity of n squared goes to infinity, so it diverges. The summation of n plus 1 over n So limit as n approaches infinity of n over n plus 1 over n. So it diverges because the limit does not equal 0. We'll look at C. The summation as n equals 1 to infinity of negative 1 n plus 1. So we'll look at the limit as n approaches infinity of negative 1 n plus 1. So this oscillates. When n is even, it's negative. When it's odd, it's positive. So it does not exist. Therefore, it diverges. Because it doesn't equal 0. Negative n to n plus 5. We have the limit as n goes to infinity. Oops, negative n. So negative n to n plus 5. We divide everybody by n. So we have negative n over n, 2n over n, 5 over n. So it's negative 1 over 2 plus 5 over n. As n goes to infinity, we end up with 1/2, which is not equal to 0, so it diverges. Example 8. The series 1 plus 1/2 plus 1/2 plus 1/4 plus 1/4 1 over 2n plus 1 over 2n plus 1 over 2n. So 4 times 2 times 2n times. Because diverges because the sum continually increases on each set of fractions. So it doesn't equal 0, it doesn't reach a finite number, it keeps on increasing. So as those keep on increasing, it reaches infinity and therefore it can't get any further. It diverges. Let's see how many more we have here. Oh, cool. All right, let's look at combining series now. When you have two converging series, you can combine them term by term. A1 plus B1, A1 minus B1, A1 times B1. Division is another story. That brings us to theorem 8. If this first sequence or series converges to A, and the second converges to B, then we have the sum rule. And we have the difference rule. Summation of A sub n minus B sub n, summation of A sub n minus summation of B sub n equals A minus B. Constant multiple rule. The summation of K times A is same, take that constant term, which is KA. Here's a corollary. To theorem 8. This is in addition to that. Every non-zero constant multiple K of a divergent series diverges, and 2. If the summation of A sub n converges, and the summation of B sub n diverges, then the summation of A sub n plus B sub n diverges. There's one apple ruins the bundle. All right, so let's get example 9. Find the sum of the series. Now I have 6n minus 1, 3n minus 1 minus 1. All right, let's see if there's anything else after this one. Yeah, reindexing. Okay, we find the sum of the series. For this first one. We have the summation and equals 1 to infinity. Since it's a monomial, we can split them up. And since it's a difference rule, we can. So we have 3 of those. So it becomes 3/6 n minus 1. So it's 1/2 n minus 1 minus 1/6 n minus 1. So A is equal to 1. A is equal to 1. R is equal to 1/2. R is equal to 1/6. So we could do A 1 minus R. 1 minus 1/2 minus 1 minus 1/6. So 2/2 minus 1/2 is 1/2. 6/6, that's 5/6. Flip that, that's 2 minus 6/5. So it's 10/5 minus 6/5 is 4/5. This one we have a constant multiple on top. So we have 1/2 to the power n. A is equal to 1. R is equal to 1/2. So that becomes 1/1 minus 1/2 times the coefficient out in front. One, flip the bottom. Okay. All right. Let's see if there's any more. Nope, the only thing we could do, last thing we do in this section is called re-indexing. As long as we preserve, as long as the orders of the items stays the same, we can index the series anytime we want to. And doesn't change the convergence or not. So for example, if we had we could change, instead of 1, we could change it to 1 plus h. And this one would be n minus h, because when we plug in n is 1 plus h minus h, we still have to have, our first term has to be a sub 1. The next one has to be a sub 2. All right, so, or if we did summation of n equals 1 minus h, then this would be n plus h, because again, this plus this has to give us a sub 1. So that's the indexing. It's not going to change anything. Example 10. So we have this geometric series n equals 1 to infinity of 1 over 2n minus 1. So when n is 1, that's 2 to the 0, it's 1. When n is 2, it's 1/2. When n is 3, it's 1/4, 1/8, and so on and so forth. We can rewrite the index as the summation of, another summation of 1 over 2 to the power n. Because when n is 0, 2 to the 0 is still 1. 2 to the first is 2 to the second, 2 to the third. Or we could do it 1 over n, 1 over 2 to the power n plus 6. So remember, we need the first one to be canceled out. So it has to be -6. -6 plus 6 is 2 to the 0, which is 1. N equals -5 plus 6 is 1, so it's 1/2. So we can do that. All right, that does it for the infinite series.